So what is that main difference between standard volumes and VDBs? When you think about it, a volume stores lots of data. Seriously, lots. Think of it. When you look at a volume containing 10 by 10 by 10 voxels, you already have to store 1,000 values. And a 20 by 20 by 20 volume already contains 8,000 voxels. When specifying an SDF, is there a way to store actually less voxels? Well, there is, and the idea is really simple. Let's just specify a maximum distance a voxel can have to a surface, and just get rid of those voxels that are too far away from the surface, and then store only values in the voxels that are really close to the surface, because you don't need more to define where a surface actually is. That is the broad general idea behind VDBs. And there are several really smart ideas that make this implementation possible. For example, the data structure in which VDBs actually store voxels. A data structure that allows for certain parts of a volume to be omitted, to be empty actually. Also, VDBs are multi-threaded and they're open sourced. In short, they are pretty awesome. So let's go ahead and directly create a VDB from this rubber duck test studio by dropping down a VDB from Polygon's node. Wire this up in here, highlight it, and we see we immediately created this SDF VDB of my geometry here. Let's dial down the voxel size, and you see this is really fast, and you can't see any of those artifacts. And even if I drop down the volume slice here, I would not get artifacts. So it's really robust when creating an SDF. It's really fast. Let's dial down the voxel size even further. And you see, we immediately get this volume here. Also, of course, VDBs can store a scalar, so let's increase the volume size a bit and check fog VDB here. And what we now get is a density field. So each voxel now stores a density. Let's drop down a volume slice to visualize that, and we can see here this is our density field ranging from 0 to 1 on the inside. What we have to take care of in the VDB from Polygon sub is these two parameters here, exterior band voxels and interior band voxels. And what that specifies is the distance from the surface that the VDB from Polygon's node allows voxels to exist in order to speed up the calculation in the VDB and of the VDB. So if we increase this here, we can see this color gradient protrudes into the interior even further. And if we check fill interior, it protrudes right to the center. So we are now storing not only values around the surface area of my geometry, but throughout the whole volume of the surface area. Otherwise, if we don't want that interior filled, Houdini automatically assumes a value of 1 on the inside of a volume, where it leaves the interior band voxels, and a value of 0 where it leaves the exterior band voxels on the outside of the volume. So that's really handy to quickly create scalar fields, scalar volumes. But let's go back and create a distance VDB, a signed distance field, and let's have a look at some of the nodes that VDBs offers me. For example, the VDB Smooth SDF. And the VDB Smooth SDF, in contrast to the VDB Smooth, is specifically there for smoothing out geometry. So let's highlight that, and you can see we can quickly dial up either the filter voxel radius or the iterations and thus smooth our geometry. And it's really staying interactive and remaining quick in contrast to the standard volumes. Also, I could choose between different smoothing operations here. So mean value is just the mean value of the voxels within that radius. It says that Gaussian is like a Gaussian blur, where the center value gets weighted differently than the values further away from a center voxel. And you also get to choose between different smoothing operations. Another neat thing that VDBs allow me to do is to attach different attributes to the VDB volume that we're creating. Let me demonstrate. In here we have dropped down the rubber duck, and we want to uncheck add shader because that is just adding a render shader and not really affecting point colors. So in our case, let's drop down a color sub here, wire this up, highlight this, set it to point. And in our case, let's just assign a random color, like so. It's not beautiful, but it's a color. And again, drop down a VDB from Polygons here. Wire this up, highlight it, dial down the voxel size, not so far, but so far. And now the VDB from Polygons sub automatically has this field surface attributes here. And let's just hit the plus here and select an attribute. And the node automatically looks which point attributes it can find. In our case, we want to transfer the point color diffuse. That's this one here. So let's check that. And let's give this VDB a name. Our geometry surface is stored in a volume called surface. So let's call this color, and that's it. So if we middle mouse over the node now, we can see we actually created two volumes. One is called surface and is a float volume, so it's a scalar volume. And the other one, which is interesting, is the color volume, which is a vector, because in order to store a color, we need to store R, G, and B values. And the interesting distinction in comparison to the standard volumes is that VDB allows you to store a vector volume as one volume. When you think about it, a standard Houdini volume would use actually 3 volumes to store this color, so it would create a color R, color G, and color B volume, while VDBs have the ability to directly store a vector. So that's very handy, because you only have to take care of one volume when storing a vector. In order to further demonstrate the power of VDBs, let's do something which usually takes quite a bit of computational time and sometimes yields quite bad results from a mesh flow. Let's do a Boolean. Let's just drop down another test geo, for example, the pig head. Let's highlight that. Turn this into a VDB as well, like so, and drop down a VDB combine node. Wire up our duck in here and pig head in here. Let's do that properly, like so. And within this node, I can do several operations, like the standard operations that you would expect from Photoshop, for example, the add, subtract, multiply, and divide. But I have also the operations that work purely on an SDF, so on a surface. For example, the SDF union, intersection, and difference, which you usually find in bool tools. So let's pick the SDF difference here and subtract this pig head from the rubber duck and highlight the node, of course. And you can see Houdini really quickly and really accurately subtracted this pig head from our rubber duck geometry. Maybe let's move this around a bit so we can see how fast this really is. So this is almost real time. Also, of course, I could choose to only output the intersection so that it intersects both geometries, or just output the union, which would merge both volumes. And now what I could do, for example, is drop down a smooth VDB and use the smooth VDB SDF, because that makes sure if I smooth this volume now, if I smooth the surface now, that it will still be a surface later and not run into problems when smoothing over our interior or exterior band voxels. So let's drop that down, highlight it, and we can see we already smoothed the geometry here. Let's dial up the voxel radius a bit and maybe increase the smoothing iterations. We can see now we have a somewhat molten together those two geometries. Now I already hear the question, what are those interior and exterior band voxels? So let me visualize them with dropping down a VDB visualize tree. Wire this up, highlight it, and also drop down a clip so we can intersect this. And let's set the clip to work along the x-axis, like so. And what we can see now is how this VDB actually works internally. And when we zoom in, what we see here, we can see on the outside and on the inside, we only have so many active voxels, visualized here by these red and white dots. And that is a rather important fact when you're working with VDBs, for example, when smoothing a VDB. Let's disable the smooth here. If I, for example, would try to really aggressively smooth this geometry, I could run into a case where it's smooth into an area where there are actually no voxels, and that would yield surface errors again, looking a bit like the surface errors that we sometimes get from standard Houdini volumes. And what the smooth SDF sub, in contrast to the standard VDB smooth sub, does is it takes care of fixing those holes and activating voxels in areas where it smooths into. And in general, this is a thing to keep in mind when working with VDBs, that in contrast to a standard volume, by default, not all voxels in the volume are active. So when you are doing more advanced stuff, for example, writing kernels and letting kernels run over this volume, keep in mind that by default, not all voxels in the whole volume area are active. Of course, there are ways around this. For example, in our case, before we have the VDB visualize 3, let's drop down a VDB activate SDF sub. Again, SDF, because we have to take care of the special quirks that we have when storing assigned distance field. And in here, what we can do is specify the half width, that is the width around the surface, in voxels that we want to be active. So let's, for example, set this to 64. Takes a bit of time, and highlight our final node. And we can see now that on the one hand, the full interior of my geometry, as well as 64 voxels outside of my geometry, are active in this VDB. Of course, there are other ways to activate a given VDB, which I'll show you later. Also, what we could do without using that sub here is, let's delete that first, go up here where we create the VDBs and just check fill interior, and that would create a volume which is filled on the inside, and also dial up the exterior band voxels to something like 48, or as we had previously, 64. So I can see On the one hand, this way we expand the volume a bit more precisely around the surface. We don't get those 45-degree angled artifacts that we had when using the VDB Activate SDF node. On the other hand, what you might have noticed is this operation took a whole lot longer than when I dialed down the exterior and interior band voxels to say something like 3. And that is because the main advantage of VDBs is its sparseness. So the ability to have areas in our volume that are empty, that do not contain voxels. Because running over voxels and generating voxels and iterating through voxels just takes a whole lot of time, no matter if you're multi-threading or not. So the main clever idea behind VDBs is the sparse data structure, so the ability to have empty areas in your volume. Let's quickly recap the main difference between standard Houdini volumes and VDBs. As mentioned, VDBs take their main advantage from being sparse. That means not having empty voxels, not having to store empty voxels. The data structure just allows to omit them. Think of it like a Rubik's Cube with a hole in it. And that allows most operations to perform more efficiently as they don't have to work on empty voxels, so voxels that in the end don't matter for our end result. And the other thing that we've seen is the difference in the way that VDBs versus standard volumes store vector data, for example. If I want to store a volume full of this vector 859 for whatever reasons, Houdini automatically would create 3 volumes that would store the vector. That is a volume for the X, for the Y, and for the Z component, while VDBs can store vector data in one single volume's voxels. So the question is, when would you use VDB and when would you use standard volumes? Well, most of the times you would try to use VDB as they are plainly quicker, because they don't have to iterate through so much data. On the other hand, when you're performing an operation or building a setup that you know is going to operate on a whole volume, where the speed increase through the use of VDB wouldn't be that massive, because a VDB as well has to store active voxels. So if every voxel in a volume is active, the speed difference between standard volumes and VDBs becomes smaller. This would be a typical case where I would prefer to use standard Houdini volumes, because I can work on them with a different kind of toolset. And in some very efficient nodes, for example the OpenCL node, you have to use Houdini standard volumes in order to operate on them on OpenCL. So that's one of the typical cases where I'd prefer standard Houdini volumes over VDBs. With most standard geometry operations though, like building an SDF, modifying it, smoothing it, booleing it, I would stick with VDBs. They are much quicker and less error prone.